Okay, Chapter 3, Section 9, Related Rates. In this section, we're going to be dealing with a lot of word problems. So it's a really tough section to work through, but I'll do several examples, and hopefully you'll get the general sort of pattern that we follow to be able to do these. So for starters, why related rates? So why related rates? Say a university student is concerned that the rate of their increase in financial aid is lagging behind the increased cost of tuition and fees. So that could be a scenario we're trying to study. Or perhaps a renter is concerned that his rent is increasing faster than his take-home pay, right? Again, that could be a situation we're trying to analyze. An automobile manufacturer wants to predict how much an expected increase in cost loan interest rates will decrease her rate of sales, right? So as the interest rate for the loans increases, it becomes more and more expensive for the consumers to purchase the car, and therefore many of them are going to choose not to buy it, or maybe they just can't afford to buy it anymore and they can't get that loan, right? So as interest rates increase, for loans of cars, we could expect that the sales will decrease, and we want to study that relationship. In general, it makes sense, but more specifically, let's put some numbers to that. What kind of sales decrease can she expect when interest rates go up by 0.1%? How does that translate directly to the sales? Or another example. Union workers are concerned that the rate of increase in their wages is falling behind the rate of increase of the company's profits, right? So ideally, if the company is making more and more money, their profits are increasing. Hopefully, they're sharing a proportion of that profit with their employees. So that could be, again, something that we want to analyze, and this could be something that the union workers can use to negotiate a future contract, right? If they identify that, hey, the company's making a lot of money, a lot of profit, and a lot of that is based on our work as the employees of this company, they have a mathematical argument to make that they deserve higher wages. Okay. All right, so what do all these things have in common? So in each of these situations, there are two quantities that are changing with respect to time. The study of related rates provides a method for determining the precise relationship between the rate of increase or decrease of two quantities. Okay, so in every one of the cases we're going to look at, we're going to have a variable, or we're going to have a quantity that we want to examine. That quantity could be the volume of a liquid. It could be the cost of an item, or the number of items sold. It could be the height of somebody. It could be the length of a shadow. It could be a variety of things, right? That's what makes this section so hard, that the word problems can really come at you from different directions. So there'd be a lot of variety of quantities we might be working with, okay? So you will have some quantities that we want to analyze, whatever they may be. And then also we want to take into consideration how those quantities are changing. So look out for keywords that are the way it changes, right? So we could have the distance and then the way the distance is changing. So the instantaneous velocity, the instantaneous change, how it changes, how it moves, how it increases, how it decreases, right? So those are all keywords. In business, of course, marginal is another keyword. The marginal cost, marginal profit, marginal revenue, right? How is the revenue changing? How is the revenue increasing or decreasing, right? So these are all keywords that we use to represent the derivative, right? The derivative is the instantaneous rate of change of the underlying function. Okay, I know that's a lot, so let's just dive into some examples. So this first example will involve distances and two rates of velocities. Remember that the first derivative of a distance function is speed. The second derivative of a distance function is acceleration. So let's dive into it. So let's say we have this situation. A 26-foot ladder is leaned against a wall. The ladder slips as the top of the ladder begins to slide down the wall. As that happens, the bottom of the ladder slides along the floor away from the wall. As the ladder falls, the distance from the top of the ladder and the distance from the wall to the bottom of the ladder are both changing. Okay, so if the top of the ladder slides down the wall at 2 feet per second, that's a speed, right? 2 feet per second. That's a rate of change. At what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? Okay, so first thing, read the question once, think about it, read it again. They're all going to be really confusing. These are really hard word problems, so it takes at least twice, maybe 3 times to read it through and really think about all the moving parts. Next, come up with a nice little drawing, a little sketch that kind of connects these variables, identify what are constants, what are variables, what are they giving you, what are they asking for. So here's a great little drawing to represent this word problem. So we have a 26-foot ladder. Notice that that's a constant value, right? The actual length of the ladder is not going to change. So 26 is a constant. And then we have the distance from the top of the ladder all the way down to the floor along the wall, right? We can label that y. It's just an arbitrary selection of the variables. You can use a and b, y and x, or something more representative like w for wall and f for floor, right? Whatever you like. But of course, people love x and y in algebra, so it makes sense that we can think of this as sort of the coordinate axes, and we have a y-axis and an x-axis, so it makes sense to use y and x as well. Okay, so let's reread this problem. A 26-foot ladder is leaning against the wall. The ladder slips, and the top of the ladder begins to slide down the wall. As that happens, the bottom of the ladder slides along the floor away from the wall. As the ladder falls, the distance from the floor to the top of the ladder and the distance from the wall to the bottom of the ladder are both changing. Okay, so we have a couple of variables. We have the variable y to represent this distance along the wall, the height from the top of the ladder all the way down to the bottom of the floor. But then we also have a speed in which it is changing, right? So that's going to be the instantaneous rate of change of the y variable. And then we also have the x, which is the distance from the bottom of the wall all the way to the bottom of the ladder along the floor. That's the x distance. And then we have the way it's changing, right? How fast is it moving as it slides? I think if you can kind of picture this sliding, it probably slides kind of slowly at first. And then as it kind of builds momentum, it starts to slide faster and faster, and then really, really fast. And then just kind of like, by the time it gets to here, the ladder just kind of falls to the floor. So we can imagine that speed, the velocity at which a little dot at the top of this ladder is moving begins slowly to change, but then faster and faster and faster, and then it collapses all the way to the ground. Okay, so now if the top of the ladder slides down the wall at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? Okay, so what we need to do is come up with an equation that brings together the variables that we're working with. And as this picture implies, this makes a perfectly right triangle. So we know that we can use the Pythagorean theorem. So by the Pythagorean theorem, we know that the y variable squared plus the x variable squared is equal to the 26 squared. Okay, now we're talking about speed, so that's the way an object is moving. Distance traveled over time elapsed. Distance over time is speed, the way something is changing. So we need to take a derivative with respect to time. So we're going to take the derivative with respect to time. That's a very, very common derivative to take in many of these word problems. It's not always going to be with respect to time, so you have to be careful. That's what makes this section really hard. You know, there isn't one straightforward rule that we always use. But with respect to time is a very popular derivative that we have to apply. So let's take the derivative with respect to time of this equation, x squared equals the derivative with respect to time of this side. And, well, let's distribute this. So this is the derivative with respect to time of y squared plus the derivative with respect to time of x squared equals, well, the derivative with respect to time of 26 squared, this is just some constant. It's a big number, but it's a constant. And so we know its derivative is just going to be 0. So let's just simplify that right away. It equals 0. And now the derivative with respect to time of the variable y squared, we know through implicit differentiation that this is going to be equal to 2y and then dy dt plus, and now again with from implicit differentiation, we know that this is going to be equal to 2x and then dx dt equals 0. So now we have a new equation. Here we had an equation that involved just the distance y, the distance x, and the distance of the ladder. So we had that. And now we have a new equation that involves the distance y, the distance x, but also the rate dy dt, the way that the y variable is changing. And we also have dx dt, the way the x variable is changing. How the x variable is changing, how the y variable is changing. The speed of the y variable, the speed of the x variable. So let's read this last part again and figure out what they're giving us and what they're asking for. So if the top of the ladder slides down the wall at 2 feet per second, that's a speed for the y variable. So this is the dy dt variable. At what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? So when x equals to 10, right? That's what this is saying. So this is when x equals to 10. They want to know what is the rate of the bottom of the ladder moving. Okay, so dx dt is the question mark. That's what they want to know. And dy dt is what they gave us. Dy dt. They gave us an indication of how the y variable is changing with respect to time. They want to know how is the x variable changing with respect to time. And this is at a point when x equals to 10. Good. Okay, well, this is what they want to know. This one they gave me. This one they gave me. And, well, we don't know what this is. So what we want to do first, step 1, is figure out what this y value is at this point in time. When x is equal to 10, what is y? So we can plug it into here and solve for our variable. Okay, so let's use this formula right over here. We're going to use this, and we're going to say y squared plus 10 squared equals to 26 squared. So y squared So y squared equals to 26 squared minus 10 squared. And so y equals to plus or minus the square root of 26 squared minus 10 squared. Now it's plus or minus because when we take the square root of both sides, we get a plus or minus. But we know that in this case, the y can't be a negative. So we'll just have to adjust for that. So 26 to the power of 2 minus 10 to the power of 2. Enter. And we want the square root of that. The square root of the previous answer gives you 24. So y equals to 24. So y equals to plus or minus 24. from the math, but we know from our picture that y can't be a negative, right? Y is a distance, so we don't want the distance to be negative. So we're going to ignore the negative. Ignore the negative. And so y equals to 24. Y equals to 24. Okay, so now going back to this formula here, this is what I want to know. I want to know the dx dt. So I'm going to subtract dy, 2y times dy dt from both sides of the equal sign. And I'm going to get that 2x times dx. You know what? Actually, let me organize this a little bit better. Okay, so now going back to our equation, 2y and then dy dt plus 2x and dx dt equals 0, right? So going back to this equation here, this is what they wanted us to figure out right here. Now we know that the y equals to 24 when x equals to 10, and they gave us the value of dy dt. So let's solve for dx dt. I'm going to subtract 2y times dy dt from both sides of the equal sign. And so we get 2x times dx dt equals to negative 2y dy dt. And so now if we divide everything by 2x, we'll get that dx dt is equal to negative 2y dy dt divided by 2x. So now, of course, the 2's can reduce. And we have that dx dt is equal to negative y dy dt all over x. So dx dt is going to be equal to negative 24, that's what the y is, times the dy dt. Now we said dy dt is this ratio over here. Zoom out a little bit. The top of the ladder slides down the wall at 2 feet per second. Now, since this is kind of like our axis coordinate, usually we have 1 unit, 2 unit, 3 unit, right? So in this direction, it's increasing. And then in this direction, going up is usually positive, right? So we have like 1 unit, 2 unit, 3 unit, 4 unit, right? So going up is positive. Therefore, because this is coming down, we're going to say that the change is decreasing, right? In other words, it used to be, where did we start? It used to be 24 feet high, and then it's going to go to 23 feet, and then 22 feet, right, as it slides down. So this value is decreasing. So we say that dy dt is going to be negative 2. Right? That's important to note, that there is the sign does matter. Okay? The y variable is getting smaller, right? Using the normal, using the scale that this is 0, and then we have 1 foot, 2 feet, 3 feet, right? So it's increasing this way, and so the y variable is coming down, it's decreasing. Good. Okay, so that means that coming back over here, the dy dt will be negative 2 divided by, and then the x, they told us x was 10. So we have everything we need now, and so dx dt is going to be equal to negative 24 times negative 2, which equals to positive 48 divided by 10, which is just going to be equal to 4.8. 4.8. Okay, and so that's the way the x is changing. The x variable is changing. So if the top of the ladder slides down the wall at 2 feet per second, then the bottom of the ladder is moving away from the wall at 4.8 feet per second. Okay, so bringing it all together, we have this ladder. Its length is 26 feet. That's constant. It's leaning up against the wall. It's sliding down. And because the y variable is decreasing, we know that dy dt is negative. Okay, so the question was, if the top of the ladder slides down the wall at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? So at this particular point in time, when the bottom of the ladder is 10 feet away from the wall, when x equals to 10, the bottom of the ladder is moving away from the wall at 4.8 feet per second. That's the value of dx dt. Okay, all right, hopefully this makes sense. But like I said, these are really hard word problems. They're all a little bit different. But what they have in common is that in every single case, you got to figure out what is the quantity we're dealing with. What are the rates, right? There'll be language about the rate or the speed or how fast is it changing or how does it change. So look for the keywords change or the keywords rate or speed or margin. So all those things indicate that there is a change in the variable. That means it's derivative. You got to come up with some sort of picture. You got to come up with some sort of picture that connects, some sort of an equation that connects all these variables. Pythagorean is a very popular one, but it could also be like a formula for area of a circle or the formula for the area of a triangle. A variety of different equations might be used. And next, we're going to have to use implicit differentiation to come up with a new equation that involves both the quantity variables as well as their derivatives. Next, there will be some way of solving for the derivative that they want. Well, I should correct that. They don't always want a derivative, but most of the time is what we need. Okay, so no two problems are identical. That's what makes this section really, really tough. However, there are a lot of similarities. Okay, so let's take a look at a general plan of attack that can help you with the questions in this section. Okay, read your question. Then step 1, sketch a figure if helpful, right? Draw a little something. It doesn't have to be a great work of art, just the key points. You know, you can draw a dot to represent a plane or a little box to represent a car. Just something that just kind of describes the word problem. Identify all relevant variables, including those rates, including those whose rates are given and those whose rates can be found. So be careful when you're reading it to distinguish between a quantity, like a distance, and the way that distance is changing, its speed. So look out for keywords like the speed, the rate, how it changes, the change in, the margin is another keyword for business questions. So keep that in mind. Express all the given rates and rates to be found as derivatives. Be careful with which derivative you want to, which variable you want to take the derivative of with respect to which variable. Time is often a very popular variable to use, but that's not always the case, so be careful. Again, experience will help with that. Find an equation connecting the variables identified in step 2. So that can be hard. So think about, you know, whether they end up creating a triangle or a circle, or if there's a relationship like profits and costs and, you know, revenue functions, you know, those kinds of known equations. So come up with an equation. Then step 5, implicitly differentiate the equation found in step 4 using the chain rule where appropriate and substituting all the given values. Okay, and then finally solve for the derivative that will give you the unknown rate that you're looking for. Okay, so that's easier than said than done. Like I said, every question is going to be a little bit different. So it just takes a little bit of practice and you know, trying out different things. So let's try another one. Okay, suppose that at the moment a westbound plane traveling 120 knots is 120 nautical miles from an airport. A northbound plane traveling at 160 knots passes directly over the airport. How fast is the distance between the planes changing 1/2 hour later? Assume that the planes continue at the same speed and direction. Okay, so Your author provided this nice little graphic for it. So we have a westbound airplane. So this is the westbound airplane. So see the little arrow here, direction. So this is the westbound airplane. And then we have another airplane here heading northbound. So this is the northbound airplane. Northbound airplane going that way. And then these are the rates of change, right? This is a measurement of velocity for the airplane. 120 nautical miles per hour, knots, is the direction heading in this direction, heading westbound. So I'm going to draw my own picture because there's one more element to this, and that's time. So let's say I'm going to draw basically the same thing, but maybe not as much detail. At time at t equals to 0, when time equals to 0, then we have our airport here. I'm just going to call it LAX. And I have this westbound airplane over here. So here's this airplane, this westbound airplane, headed this way. So here it goes this way. At time 0, we know that this is 120 miles. Let's scoot over here so you can see it. 120 miles from the airport. Let's use W, the letter W, to represent the distance that this westbound airplane is away from the airport. Right? This is the westbound airplane. Okay, and then there is a speed associated with it. It's traveling at 120 knots. So that's the rate of change of W, right? How fast is W, the distance away from the airport, changing? So we have dW over dt is going to be the 120. However, we have to be careful about signs. So as time goes on, this airplane is going to be getting closer and closer and closer to LAX. Therefore, the distance W, that variable, is going to be getting smaller and smaller and smaller. It's decreasing. As time goes by, that variable is going to get smaller and smaller, which means that this derivative has to be negative. Okay. All right, now at time 0, we have this other airplane that happens to be right on top of the airport at that moment in time. So it's this airplane. This is an airplane. There's this airplane. Wow, that's really ugly, but, well, okay. It's an airplane. Okay, at time 0, there it is. It does have a certain velocity, but it's really hard to do anything with it because it's sitting right on top of the airport. So let's skip on forward because they also ask us about the distance changing 1/2 hour later. So let's scoot out a little bit more. And let me draw another scenario over here, because we have another case when LAX is here. And now 1/2 hour later, this is when t equals to 1/2 hour later, then this northbound airplane has now traveled some distance. Again, this is supposed to be an airplane, whatever, it goes that way. So northbound airplane, this is the northbound airplane. Now has traveled some distance, capital N, right? Northbound, capital N, and it has a velocity, a rate of change of this variable, and that's where this dn over dt is going to come in, and we're told that it's traveling at 160 knots. Good. And then we still have this other westbound airplane. So there's this westbound. Now it's a little closer though, because it's 1/2 hour later. It's been traveling. So now it's going to be a little bit closer. Again, this is my interpretation of a plane. Wow, that's maybe that way. I don't know. Whatever. This is the plane. Like that. So now there is some sort of distance there. W to be determined. It's not 120 anymore because it's a half hour later and this plane has been traveling. It's been getting closer. But there is a distance between the airplanes. Over here, it was kind of silly because the distance between the airplanes at this point would have been exactly the same as the distance right there, right? So the distance between the planes would have been the same as the distance between the westbound plane and the airport, which would have been 120 miles. But as we move forward, that's not going to be a constant. As we move forward in time, this airplane is going to continue to travel in this direction at a speed of dn dt equal to 160. Right, so it's traveling that way, and this one keeps traveling toward the airport, presumably stopping at the airport, or maybe it just keeps going right past it and keeps going west. We don't know. But the distance between them, this variable, is going to change. Now, we could use the letter d for distance. Seems pretty plausible. But then when we take derivatives, it's weird because we have d dt of d, so it looks pretty ugly. So we should look for a different variable. So I'm just going to use the letter a. We'll say a is that distance between the two airplanes. Good. So a equals to the distance. So let's label some of our variables to be sure of what all these things represent. So w represents a distance. Okay, so w represents the distance between the airport and the westbound plane at t equals to 0. We've established that w equals to 120. At t equals to 1/2, we've established that w equals to, oh, okay, well, we have to figure out what that is, right? It's going to be different. We'll figure that out in a second. So I'll just put it in a box right here. Yet to be determined. N represents the distance between the airport and this northbound plane. Okay, so again, at t equals to 0, n is equal to 0 because it's right over the airport. So it hasn't traveled anywhere. You know, the distance between the airplane and the airport is 0 at that point. And at t equals to 1/2, well, then it's traveled a little bit, so we'll have a value for n at that point, right? Again, to be determined. We'll figure that out in a second. We also have these derivatives running around. So we have dw dt, which is the speed or the velocity of the airplane, velocity of the westbound plane, and we have d capital N over dt, which represents the velocity of the northbound plane. And finally, we are interested in the distance change. How fast is the distance between the planes changing? So A is the distance, capital A is the distance between the planes. Capital A is the distance between the planes. And so then dA dt, d capital A, dt is exactly what we're interested in, the change in the distance between the planes. Okay, so we've established that we kind of have two different pictures going on. We have the case when time equals to 0, and then we have the case when time equals to 1/2 hour later. Now, the northbound plane is traveling at a fixed speed of 160 knots, 160 nautical miles per hour. So when t equals to 1/2, then n is going to be equal to 160 times 1/2. It's traveled, right? N is a distance. So if it's traveling 160 nautical miles per hour for half an hour, you're going to get a value of 80 nautical miles. 80 miles, nautical miles. And then likewise for W, we are traveling at a fixed speed of 120. So W is equal to, okay, you were 120 miles away at time equals to 0, and then you're chipping away at that because you're getting closer and closer and closer and closer to the airport, and you're getting closer at a speed of 120 nautical miles per hour. So if you had been traveling at this speed for 1 hour, well, you would be at the airport. But you didn't travel for 1 hour, you traveled for half an hour. So this would be W equals to 120 minus 60, which means W equals to 60 miles, 60 nautical miles. Okay, so that brings me back to this. Let's fill this out now. Let's get rid of this, let's get rid of that. We're ready to write it down. So at t equals to 0, W is 120 miles. At time equals to 0, the westbound plane is 120 miles from the airport. At t equals to 1/2 hour, 1/2 hour later, W is now only 60 miles from the airport. Okay, likewise, the northbound airplane, when t equals to 0, n equals to 0, it's right over the airport, so it's 0 miles away from the airport. Half hour later, because the plane is traveling at a fixed speed of 160 knots, then the plane is going to be 80 miles from the airport. Okay, so what about the variable a? When t equals to 0, right, let's make some space here. When t equals to 0, then that's this case over here. Well, the distance between the airplanes is exactly the same as the distance between the airport and the westbound plane. So at t equals to 0, capital A equals to 120. What about at the case when t equals to 1/2? In this triangle, what's the distance, the value of A? Let's squeeze it into here. So we could use the Pythagorean theorem that n squared plus w squared equals to a squared. And we already know that the value of n is equal to 80. So 80 squared plus 60 squared must be equal to the a squared. So the square root, and it's plus or minus when we take the square root, of 80 squared plus 60 squared must be equal to a. And of course, we get to ignore the negative. Ignore the negative. So now we can just get our calculator out and figure out the value of a. So 80 squared plus 60 squared equal to 10,000. And then we want the square root of that. The square root of answer here is 100. Okay, so 1/2 hour later, A is going to be equal to 100 miles. Right? At this particular snapshot in time, the distance between the two airplanes is 100 miles. Right? 1/2 hour later, the two planes are 100 miles apart. However, that's not what they asked us for. They didn't ask us how far away are the two airplanes. They're asking us how fast is the distance between the planes changing. So they're asking us about dA dt, not A. That's a very common source of misunderstanding for people. Okay, so next we want to bring together all the variables into something. Oh, let's fill out this guy here. This was 60 there in this one, and so n equals to 80 in this one. Okay, and A we just established was equal to 100. So at this particular snapshot in time, these are the values of n, a, and w. So let's bring all those together, again, using our Pythagorean formula. Let's put it over here. And so we have n squared plus w squared equals to a squared. And now we're going to take a derivative with respect to t of everything. N squared plus w squared equals the derivative with respect to t of the a squared. Okay, so now using implicit differentiation, we can figure out that this is equal to 2 capital N dn dt plus 2w dw dt is equal to 2a dA dt. Okay, so we have a new formula here, and the advantage of this formula, the great thing about this formula is it contains the variable or the value of interest, the rate of interest. They asked us about dA dt, the speed with which the distance between the two planes is changing. So that's the one we want to know. And everything else we have. At this particular point in time, n, we said n is equal to 80. Dn dt, well, we have that. That's equal to 160. W, well, that's equal to 60. And dw dt, well, that's equal to negative 120. Did I put that somewhere? Oh, yeah, here it is. Negative 120. We established that the sign is important. And a, we established a was 100. So we have everything we need here to solve for this value, this rate. Okay, so let's make a little more room. So solving for dA dt, all I'm going to do is divide everything by 2a. So I'll get that dA dt is equal to this whole left side divided by 2a. So it's 2n dn dt plus 2w dw dt, all of that divided by 2 capital A. Okay, so now we've got every single one of these values. We can solve for our rate. So 2 times n, we said n is right here. It's equal to 80. Times dn dt is equal to 160. Plus 2 times w, and the w we said was 60, times dw dt, and dw dt is negative 120. And all of that gets divided by 2 times a, which is equal to 100. Okay, we punch that into our calculator. Let me put that over here. That means that dA dt is going to be equal to 56. Okay, so this means that the distance between the planes is changing. It's increasing, right? Because it's positive. It's increasing at a rate of 56 knots. So let me box that up over here. So the distance between the planes is changing at a rate of 56 knots. Good. Okay, so again, read your question, read it again, read it a third time, make sure you get a pretty good understanding of what they're describing. Start drawing pictures. Doesn't have to be a perfect picture, just something to kind of represent the various quantities in question. Start labeling your variables. I would describe the variables off somewhere because it's easy to forget whether w was supposed to be a distance, whether w was supposed to be a quantity, it could be a variety of things. So label them. make sure that you are clear if there are two different snapshots in time. So you might want to do more than one picture like the way I did here. There might be another word problem where they say something like 45 minutes into the flight, blank, 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 and then 3 hours later, blank, blank, blank. So you have two different snapshots of time. And so the same variable might have two different values at two different points in time. Right? So you might need different pictures. So keep those straight and keep those in mind. Usually, just sort of by practice, once I've established my quantities and I established my variables, I know that I'm going to be interested in derivatives of those. Often it's with respect to time, especially if you're talking about, well, very often it's a very popular a very popular request in these types of problems to find the derivative with respect to time. So be careful which derivative you're asked to use. I try and figure it out based on what information they've given me. So I knew that this involved a derivative with respect to time because they gave me a speed, a velocity, right? So that automatically lets me know that's what I'm dealing with. Okay, and then, some people jump to setting up the equation and then kind of reverse engineer it and think about all the things they're going to need. They're going to need an n, they're going to need a dn dt, they're going to need a w, they're going to need all these things. And then they kind of go back and find them. So it just depends on your style. And every word problem is a little bit different. So, you'll develop your own kind of systematic approach. Just try and be neat. I know this is pretty messy as well. I'm still getting used to this method, this working with this software program here. If we were in an in-classroom setting, I think I'd do a better job of organizing my board work and putting it all nice and neat on the board. But this isn't too bad. Okay, all right. Hopefully this one makes sense. Let's move on to another one. Okay, suppose a point is moving in a circular path centered at the origin and radius 5. The graph has the equation x squared plus y squared equals to 25. When the point is located at -3, 4, so that's in quadrant 2 somewhere, its x-coordinate is increasing at a rate of 0.4 units per second. How fast is the y-coordinate changing at that moment? Okay, so let's start by doing a little picture. So here's a nice graphic your author provided. Okay, so we have a nice circle centered at the origin. The radius is 5 units. Let's put it in here, put it in green. So we know that the radius from here to any point on that circle, the radius r, equals to 5. And so any point on that circle, and that circumference, is going to obey this rule, right? This is the equation of a circle, x squared plus y squared equals to 25. So here's a particular point. We can confirm that that's a point on this line. Let's confirm it. So let's see, if we plug in blank squared plus blank squared equals 25, and so if we let x equal to -3 and y equal to 4, we get -3 and 4. That makes it a 9 plus 16 equals 25. Yep, that's true, right? So any point that's on this curve, any value a comma b that's on this circle must satisfy the equation, right? That's what this formula represents. Okay, when the point is located at -3, 4, so you're in quadrant 2, you're right here, its x-coordinate is increasing at a rate of 0.4 units per second. How fast is the y-coordinate changing at that moment? Okay, again, they've given us a change, a speed. It's increasing at a rate of 0.4 units per second, right? So we know it's over time. So they've given us the x-coordinate, that's -3. They've given us the y-coordinate, that's equal to 4. And they've given us dx dt. the way that the x variable is changing, and that's equal to positive 0.4. So we have these three things, and what they're asking for is how the y-coordinate is changing. So I know that it's dy dt that they're interested, right? That's the question mark. This one's going to be an easy one, way easier than the one before. So if we have x squared plus y squared equals to 25, let's take a derivative with respect to t, right, inspired by the information they've given me and the information that they asked for. Let's take the derivative d dt of x squared plus y squared, and then on the other side, the derivative with respect to t of 25. Well, that's going to be easy. This is a 0. So this is going to be equal to 2x dx dt plus 2y dy dt equals to 0. And so this is the variable of interest. We can divide everything by 2. Divide this side by 2, divide that side by 2. And so it'll cancel here, right? Factoring those guys. And so, let's bring this over here. We have x dx dt plus y dy dt equals to 0. Remember, 0 divided by 2 is still 0. And we're interested in this variable, so let's solve for it. Moving this term to the other side, we get y dy dt is equal to minus x dx dt. And now if we divide everything by the y, we'll get what we want. dy dt is equal to negative x dx dt divided by y. Good. Okay, so we have everything we need. Let's plug it all in. We get that x is negative 3, so we have a minus from out here, and then the x itself is also a negative, so we're going to have a minus there and a minus there. Dx dt, that's equal to the 0.4 divided by the y, and the y was a 4. So now if we multiply that all together, we should get that this is equal to 0.3. Okay. So bring it together, the dy dt equals to 0.3 units per second. So the y-coordinate is increasing. So when the point, put a full sentence here, when the point is located at negative 3 comma 4, the x-coordinate is increasing at the rate of 0.4 units per second. That was given. I haven't found, that's nothing new. And then the part I'm going to contribute is that at the same time, when the point is located at the point negative 3 comma 4, so this is the part we found, the y-coordinate is also increasing at a rate of 0.3 units per second. Right? And I knew it was increasing because it's a positive value. Remember, the sign makes a difference. If all of this turned out to be negative 0.3, then I know that it would be decreasing at that moment. Okay, so read your question, draw a picture, come up with an equation that connects the variables, the quantities of interest. Sometimes that's really obvious, like it is here in terms of the circle. But it might be a question that involves the area of the circle instead, or it might be a question that involves the circumference of the circle, the distance traveled by a point going in a circular direction. It could be a variety of things. So you have to be careful. Every question is going to be just a little bit different, and that's why this section is really challenging. Okay, a spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Okay, so Carefully read it once. Make sure you kind of have an idea of what's happening. Maybe read it twice if you need to. Let's draw a little picture to try and kind of figure out everything. So we have some sort of a little spotlight. I'll put it in on the ground. So let's see. Here's our ground. And then we have a wall. A spotlight on the ground shines on a wall 12 meters away. Okay, so let's say that the spotlight is on the ground. It's right here. Let's make it in red. Here's this tiny little spotlight shining this way. And it is 12 meters away, so that sounds like a fixed value. So this is 12 meters away from the wall. And then a man that is 2 feet tall, let's make the man in green, a green man, 2 feet tall, walks from the spotlight toward the building. So let's say here's the man. And his height's going to be fixed as well, so that sounds like a fixed height. Let's make that 2 meters. 2 meters. And so we see that this light is going to reflect from the top of this guy. So at this point where I drew it, this would come through here, touch on him there, and kind of make it all the way up to there. So at this point, if this is the man right there, then this would be his shadow, right? And then as he walks closer and closer and closer to the wall, then we can see that the line connecting the top of this light here to the top of his head to the wall, that light's going to get, that shadow is going to get smaller and smaller and smaller, right? So for instance, at some point, his height stays the same, so at some point he's like way over here, much closer to the wall, right? He's still 2 meters tall, so that doesn't change, 2 meters. But at this point, the light would go from there and then connect to the top of his head. Messed it up. Would go from there, connect to the top of his head, and go there. So at this later point, when he's closer to the wall, the shadow would be smaller. So we can see that the shadow is going to be decreasing as the man walks closer and closer and closer to the wall. Eventually, if he keeps going, he'll walk right up to the wall. And at that point, well, his shadow will be exactly 2 meters tall. Right, so we get a sense of what's happening. This man is walking toward the wall. His height stays the same. The distance from the light to the wall stays the same. And we're interested in shadows. Okay, so let me erase this part here and go back to that more simple diagram before we had those things. Okay, so we're going to need something about the distance the man is from the wall, and we also need something about this. So let's call, well, I could call it x. So let's call this distance right here x. Call this distance x. And now we could call the distance, so this is the distance from the light to the man, right? And we know that that's going to get bigger and bigger and bigger as he's walking this way, right? This man is walking in this direction. So we know that x is going to be increasing. And then the distance between the man and the wall, we could label it some other variable, a or b or something like that. But whenever you can minimize the number of variables, you want to take advantage of that. Use as few variables as you can, right? Just the bare minimum of what you need. Otherwise, you just have an unwanted number of variables that just makes things unnecessarily complicated. So even though there's perhaps a desire to want to throw in another variable for this, let's use the fact that the 12 is fixed, and so if x represents the distance from the light to the man, then the distance from the man to the wall, this distance right there, should be 12 minus x. Okay, let me make more space there actually. So that means that this is 12 minus x, and then that entire distance from there all the way out to there, that was the fixed distance of 12 meters. Okay, we're also going to need something to represent the shadow, and well, we tend to have this horizontal, vertical. It just seems to make sense to think of this as y. So let's y represent the height of the shadow. Right, let's label our variables here. So y equals the height of the shadow x represents the distance between spotlight and the man. And then, of course, that means that 12 minus x equals the distance between the man and the wall. Okay, so now let's read it one more time, make sure our picture continues to make sense, and try and figure out what information they're giving us and what do they want to know. So a spotlight on the ground shines on a wall 12 meters away. If a man that is 2 meters tall walks from the spotlight toward the building at a speed of 1.6 meters per second. Okay, so now let's tackle this speed thing. That's the speed of this man. This man is walking in this direction, right? His speed in this direction, speed, is 1.6 meters per second. Okay, so that is a rate of change. And it's a rate of change of both of these two quantities, right? There is the distance from the spotlight to the man, and there's also the distance between the man and the wall, right? Both the yellow and the blue are affected, right? If he's standing still, there's a constant value there. Like let's say, for example, x equals to, at one point x equals to 2. At one point, 8x might be equal to 2, which means that the blue distance over here, one point x might be equal to 2, so maybe this yellow distance is 2, which means that the blue distance is 10. They have to add up to 12, right? So if he's standing still, those are the two values, but then as he's moving, then the 2 will increase because he's walking away from the spotlight, and the distance between him and the wall will decrease because he's walking toward the wall, and the rate at which those two things change is exactly the same, right? His speed away from the spotlight is the same as his speed walking toward the wall, right? I mention that because the way I've written it here, it's more convenient to think of it as the speed, the way that x is changing. Right? Just because dx dt is a little easier to work with than the derivative with respect to t of this variable, which we didn't even use a single letter to represent this blue quantity here. We used 12 minus x, which we could work with, but it just makes more sense, I think, to think of it this way. Okay, so what we have, this given value of 1.6 meters per second then represents dx dt, the speed at which the man is moving, and that is given, the speed of man walking away from spotlight, which same as speed of man walking toward wall. Right? The speed at which he walks toward the wall is the same thing as the speed at which he walks away from the spotlight. Okay, so then dx dt specifically is the rate of change of the x variable, the rate of change of the distance away from the spotlight. Okay, so that's the 1.6. Okay, now how fast is the length of shadow on the building decreasing when he is 4 meters away from the building? So how fast is the shadow changing? That's what they're interested in. So dy dt is the question. Dy dt is what they want to know. And this is when he is 4 meters from the building. This is find this rate when the man is 4 meters from the building. And note that we're expecting the y to be getting smaller and smaller and smaller, so we're expecting this value to be negative. So that could be one quick little check to make sure that we're doing things well. So also, when he is 4 meters away from the building, that would mean this distance from here to here, right? When that distance, when the man is 4 meters away from the building, keeping in mind that the whole thing, the whole distance is 12, at that point, he would be 8 meters away from the spotlight, right? So let me recreate that triangle over here, and we'll find, let's recreate this right in here. So let's say we have this, and we have the light source coming from here to there, and we have the 2-metered man. So let's say the 2-meter man is here. So this is the 2-meter man. And we're saying that at this particular point in time, the distance between the man and the wall is 4 meters. Because the whole thing is 12 meters, right? We have 12 minus 4. We know that this, from here, from the spotlight to the man, that distance must be an 8. And of course, we don't know this height. That would be the shadow. So the shadow would be this y. And of course, the whole thing is 12 units. So let me just go ahead and note or highlight that that's 12 units. Okay, note that we could think about this as two separate triangles. There is this triangle from here to here, this little yellow one here. This is a right triangle. So let me draw that. I'm gonna separate them. So this yellow triangle, I'm gonna put it over here. Goes like this, goes like that. It's a right triangle. We know that this length, this leg is 8, this one is 2. We don't know the hypotenuse. That's okay. And then let's think about this big triangle, right? So this yellow triangle is nested inside this much larger triangle. It's also a right triangle. Its height is y. It's the shadow at that point in time. This leg is 12. We also don't know the hypotenuse. We do know, however, that this angle here must be the same as this angle here, right? Because one triangle is nested inside the other. That means that this is theta. It's the same angle in all three drawings. Good. And since they all share this 90 degree as well, then it must mean that whatever angle that is, it's the same in both cases. So what we've established is that these two triangles must be similar triangles. Right? That's because they share the same three sides. So because they're similar triangles, we can establish that, for example, y divided by 12, this leg divided by that one, is equivalent to the ratio of this one divided by that one. Okay. Now, if we multiply both sides, we get that y is equal to 2 divided by 8 times 12. That's going to be 24 divided by 8. It's going to be equal to 3. So we've established that at this point y equals to 3, which means this shadow equals to 3. So we've established that when the man is 4 meters away from the wall, his shadow will be 3 meters tall. The shadow is 3 meters tall. Okay, that's very useful to know, but not quite the answer to the question they asked. They didn't say how tall is the shadow at that point. They asked us, how fast is that shadow decreasing? Okay, so let's get back to the larger image over here. Okay, I want to do something very similar to this. I want to take this more generic picture that we have here and separate the two triangles. So I'm going to come back up here. I'm going to do the same kind of thing where I have this smaller triangle in the tip here. So it's going to be this little triangle. And then this larger triangle. They both share a right angle, both right triangles. This one is going to represent the height of this one is going to represent y, which is the shadow. The height of this one represents 2, which is the height of the man. We know that this leg is going to be x, and we know that this whole thing here is the constant 12. So it's very similar to what we did over here, except here I'd locked in the fact that the man was 4 meters from the building, and therefore x was equal to 8. Okay, so here we're just leaving it in general as the man walks. And then again, we know that they both share this angle theta, so this must be the same angle for all 3 pictures, and therefore they must share that angle as well. So again, we have a case of similar triangles, just like before. So just like before then, we can establish that, let's put a line there, that y divided by 12 must be equal to 2 divided by x. Multiply both sides and we get that y equals to 24, well, 2 times 12 divided by x, or y equals to 24 divided by x. Okay, so since we're interested in finding dy dt, let's take a derivative with respect to t. Derivative with respect to t of the y. And then I'm going to separate that 24 and say it's 24 times the derivative with respect to t of the 1 over x. Let me zoom in here for a little bit. So this is exactly what we're after. This is going to be the dy dt equals to 24 times, and this is the same thing as d dt of x to the negative 1 power, which means that dy dt is equal to 24 times negative 1 times x to the negative 2 power times dx dt. And so from here, we can conclude that dy dt is equal to negative 24 divided by x squared times dx dt. So we have a formula for the derivative we're interested in. So we're almost there, not quite done. Now we have to plug in the values we know. So at a particular point in time, when the man is 4 meters away from the wall, we already know the value of x is equal to 8. And we know dx dt, so we can plug in these two values and get the result we want. Okay, so let me zoom back out over here. Okay, so now let's take this over here and say when the man is 4 meters from wall, We've established that means that he is 8 meters away from the spotlight. Good. And that's the value of x. So now we also established that dx dt is given as 1.6. So we got everything we need. dy dt is going to be equal to negative 24 divided by 8 squared times 1.6. And then we just plug that into our calculator and we'll get the desired result. dy dt is equal to negative 0.6 meters per second. Okay, so that means that the shadow is decreasing at a rate of 0.6 meters per second. Okay, so when the man is walking toward the wall, he's 2 meters away from the building. We know he's going to cast a shadow that is 3 meters tall. And at that particular point in time, that shadow will be 3 meters tall, but decreasing and decreasing at a rate of 0.6 meters per second. Okay, a boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, so we have this nice little picture provided by your author here. So we have a boat, it's being pulled into the dock. Here's the pulley right in there. So we have the distance between the boat and the base of the dock along the water. So we have that. We have this distance of the rope, the length of the rope. And then, of course, we have the height. So we can represent all of this with a simplified picture that just looks like a triangle. Comes up, comes like this, comes across. And from here, we know that the dock, this is 1 meter. That's fixed, 1 meter. And this is a variable that changes. It's the distance from the boat, the tip of the boat, all the way out to the base of our dock. Let's call that variable x, kind of being consistent with horizontal variables tend to be x, vertical variables tend to be y. I just need a variable in this case here because this is a constant, right? The height of the dock doesn't change. But I do need a variable in this direction. Usually we like to deal with hypotenuse as h, so why don't we let this variable here, this distance, the length of the rope, let's let that be h. H is the length of the rope. Okay, let's read it again. A boat pulls into a dock by a rope attached to the bow of the boat and passing through the pulley on the dock that is 1 meter higher than the boat. If the rope is pulled at a rate of 1 meter per second. So the rope is being pulled by this pulley, and so the distance of h is getting smaller and smaller and smaller, right? The length of the rope is getting smaller and smaller and smaller, and that's what this is referring to, right? So dh dt is equal to the rope is being pulled at a rate of 1 meters per second. Now keep in mind that this speed is acting, this rate is acting on the variable h, and as time goes by, h is getting smaller and smaller and smaller, so it's decreasing. That's how I know that this has to be a negative. This has to be a negative 1 meters per second, right? And this is the speed of the rope. So this is the velocity of the rope. Velocity of the rope. Okay, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, so this is when x equals to 8, when the boat is 8 meters from the dock. How fast is the boat approaching the dock? find the speed, the change of the variable x. So they want you to find this thing. Okay. So a nice way to connect these two variables, we have the variable h and the variable x. Well, it's Pythagorean, right? So we can establish that x squared plus 1 squared must be equal to h squared. From here, we can find the value of h when x equals to 8. So when x equals to 8, we'll have 8 squared plus 1 squared equals to h squared, which means that this is going to be 64 plus 1 is 65. So 64 plus 1 equals the square root of h, or 65 equals h squared, or you can say that h is equal to plus or minus the square root of 65. And of course, h is this length of rope, so we can ignore the negative. And so at this point, h equals root 65. We can turn it into a decimal just to get an approximation of what this is. So it's a little bit more than 8. 8.06, we'll say. Okay, so we've established that when x is 8, when the boat is 8 meters away from the dock, the length of the rope is a little bit more than 8, approximately 8.06-ish, but we can just leave it as root 65 to get an exact answer. Okay, of course, that's not what they asked for. They asked for dx dt. How fast is that distance changing? What is the rate of that change? How fast is the boat approaching the dock? Not how far away is it? Okay, so let's go back to this formula. Going back to the formula that connects the h and the x variable together, we have that x squared plus 1 equals to h squared. Well, you know what? Let me flip it around. Let's say that h squared equals x squared plus 1. And I'm going to take a derivative with respect to t. So d dt of h squared is equal to d dt of x squared plus 1. So using implicit differentiation, this is going to be equal to 2h times d dt of the h variable equals 2x times d dt of the x variable, or simplifying it, divide everything by 2. Let's divide this side by 2, divide that side by 2. That cancels, that cancels, that cancels, that cancels. And so we'll get h times dh dt is equal to x times dx dt. Okay, so now dx dt is what they were asking for. Let's zoom back out. They gave us the dh dt value, and we were able to figure out the value of h at a specific point. When x was equal to 8, we found out that h was equal to root 65. So we have everything we need. Let's move this guy up here and say that dx dt, what they asked us for, is then equal to h times dh dt divided by x. Okay, so dx dt is equal to h, which was root 65, times dh dt, which is equal to -1, divided by x, which we said was 8. So dx dt is equal to -root 65 divided by 8. So again, we can get our calculator and do an approximation. So dx dt is going to be equal to approximately negative 1.01 meters per second. Thus, the boat approaches the dock at a rate of 1.01 meters per second. Okay, a trough is 10 feet long, and its ends have a shape of an isosceles triangles that are 3 feet across at the top and have a height of 1 foot. If the trough is being filled with water at a rate of 12 cubic feet per minute, how fast is the water level rising when the water is 6 inches deep? Okay, so the first thing that kind of pops to my head when I see this is the units, right? You got to make sure. Sometimes these things are in meters. This one's in feet. Sometimes it's in hours, and this one's in minutes. But then I see that there is a units are being given in feet, then all of a sudden it's being given in inches. So let's make everything match. I could change everything to inches. That wouldn't be hard there. That wouldn't be hard. But then they gave it to me in 12 cubic feet per minute. So let's just right away, first thing, change this to feet. So just right away, I want to change this right here to say, okay, that's the same thing as saying half a foot. 6 inches equals to half a foot. Okay, so let's make sure we don't make a mistake there. Okay, a trough is 10 meters long, and it's got triangles, the shapes. So it'll look something like this. Maybe have a triangle kind of coming down like this. And then this kind of goes that way. Like that. Something like that. There. Right, something like that. So you can imagine, hopefully imagine this. And then of course there's water being filled. So here's the water line like this. And so inside here we have water. What happens here? I guess this kind of comes down here, like that. Okay, so we have water and highlight that water like this. Water like that. Okay, close enough. So here's our trough. It's got triangles, and there's this water being filled. This rate right here, 12 cubic feet per minute, that's a rate of the volume, right? The volume of water. Let's let V equal to the volume of the water. Let's define V to equal the volume of water. So therefore, dV dt is the rate of which that volume is increasing, which is the rate at which the trough is being filled. So this is equal to 12 cubic feet per minute. And water is pouring into it, so it's positive. Note that if this was a different word problem where they said maybe there was a hole or something, or is being pumped out of here, then the volume would be decreasing, and so therefore this would be negative in those cases. But here we're putting water into it, the variable volume V is going up. It's increasing over time, so I know that this better be positive. Okay, so I did a nice little picture here, but I want to kind of focus on just like a, kind of a section here. If we slice it off, we would end up with two kind of triangles here. So if I have, oops. So if I just kind of think of a cross section, if I come here and just kind of slice this off like this, and just kind of come through and slice it off, and then pull it off to the side over here, I would have two triangles that I'm working with. I have this bigger triangle like this. It's a cross section of that triangular trough. And then I have this smaller triangle, let's put it in blue, that represents that waterline. Okay, so we know that the trough is 10 feet long. So this distance there is 10. And that's a constant. That doesn't change at all. 10 feet. And we know the height of it is going to be 1 foot tall. So one foot. So that means that this height right here, from here to the floor, is also going to stay constant. That's 1 foot. And it's at the very top, right? The very top is 3 feet across. So from there all the way out to there, 3 feet. So the shape of the container stays the same. 1 foot height, 3 feet wide, 10 feet long. It's really the water one that's going to change as we've put in more water. Well, the length is going to stay the same, right? If I just think about the volume of water, this length is still going to be 10. What changes is this triangular values. So there's going to be a base this way, which we don't know. A base going this way, well, let's just label it B then. B. And then we have a height, and then again, this height, I don't know what this height is. Height of this guy, I don't know, let's label it H then. Okay, so I have these two triangles. Let's think about the following. They're going to be similar triangles, right? And if you like, we can also think about, well, for a variety of reasons. I'm going to cut them in half. So if you think about cutting this in half, think about cutting that in half, you end up with a right triangle. And if you cut this guy in half, you also end up with a right triangle. Now, they shared this angle before, right? The shape of the trough. Of course, they have this angle in common. They have this angle right there in common. That angle is the same as this angle, which is the same as this angle. Good. And if we cut it in half, that means that this angle over here, let's put it in purple, that means that this angle over here must be the same as this angle over here. And so now they share this angle. If I'm focusing on the triangle to the left here, so I'm just going to focus my attention for a second on this triangle here. And of course, this triangle here. We've established that this little angle here must be the same. And they both are 90 degrees, so therefore that must mean that this angle up here is also the same. So this must be the same as this one. This angle, let me zoom in a little bit more. Okay, so again, walking through the logic here, if we look at our shape here, this angle here in green, whatever that angle is, must be the same angle when you think about the entire shape of the container, that shape, and the shape of the angle of just the blue water part of it. So this whole angle must be the same as this whole angle. And so if I cut it in half, dissect it exactly in half, it must mean that this angle here in this little purple, in fact, let's give it a name. Let's call this angle alpha. Then this angle right here must also be angle alpha, right? They have to have the same angle. They also share this in common because this is 90 degrees. So this is also 90 degrees. And since those two angles are the same, it must mean that this final angle here, whatever this angle is, let's call it angle theta, must be the same for both of them. This one must also be angle theta. So we established that these two are similar triangles. So I'm going to separate them out. So I have this. Now it's cut right in half. It's a right triangle. And if the whole thing here is 3, then half of it must be 3 divided by 2, or 1.5 feet. Good. Now the height stays the same, even if you chop it in half. So this height right here must be 1 foot. Good. And then coming over here, teasing out this little yellow triangle, I have this, like that. Again, this is a right triangle. And the h stays the same, the height. And now in this direction, well, that must be half of b. And these two are similar triangles. Similar triangles. So because they are similar triangles, it must mean that I can say that this leg divided by this leg is equal to this leg divided by this leg. So I'm going to say that 3 divided by 2 over 1 must be equal to 1/2 b divided by h. Good, good, good. Okay, so now if I simplify all this, I get that 3 divided by 2 must be equal to b divided by 2h. And if I multiply both sides by 2h, multiply this side by 2h, multiply this side by 2h, I get a value for b. These two cancel, and then these two cancel. So we get that b, I'm just going to flip it around, b equals to 3 times h. Okay, that's useful, but not quite done yet. That's not the answer we were looking for. So we've established that b equals to h. Okay, b equals to 3h. Okay, so now thinking about the formula for the volume of the water. The volume for the water, the volume is going to be equal to the area of a triangle. Area of a triangle is always 1/2 times the base times the height. That'll give me the area of the triangle. So I'm thinking of the water line. So I know if you do a cross section, it'll be a triangle. So this will be the area of that triangle. And then if we multiply it by the length of the trough, we'll get the volume of the water. So volume is equal to 1/2 times the base. Well, using this notation here, we're saying that this is the b, and then the height is h. So b times h times the length, and well, the length is constant. It's just 10 feet long. So if we multiply 1/2 times 10, we'll go ahead and get that the volume is equal to 5BH. Okay, so perfectly good answer, except we have 3 variables here, the V, the B, and the H. One too many, so luckily we can use this right here to reduce it. So we can say that V is equal to 5 times 3H times H, where I'm replacing the B with 3H. So that means volume is equal to 15 times H squared. Good. Okay, so now let's take our derivative with respect to time, because they gave us a rate at which the volume was flowing into this trough. So now if we do d dt of v equals to d dt of 15h squared, we'll get that this is going to be dv dt equals to 15 times 2 times h times dh dt. And this is exactly what they were looking for. They gave us the volume, the rate of the volume, how it's flowing, how much water is flowing in, the rate of the water flowing into the trough. And they gave us this. So now we just need to find h. So let's see. Did they give us h? A trough is 10 feet long, and its ends have a shape of an isosceles triangle that are 3 feet across, the top of 100 meters. The trough is being filled at a rate of 12 cubic feet per minute. How fast is the water level rising when the water is half a foot deep? Okay, so that's when h, right? So this is the value of h. So running out of space over there, so I'm going to squeeze it into here. We have everything we need right here. I'm just going to go ahead and solve for dh dt. That's what they wanted us to find. So dh dt is going to be equal to dv dt divided by 30h. Okay, so we're going to box that up and we're going to use it over here. Find how fast the water level is rising. So that's the rate of the height of the water line, right? That's the h. Find dh dt. So now we can say that this is when dv dt is equal to 12 and h is equal to 1/2. And so we have that dh dt, which was equal to, it looks kind of ugly like that. So I'm going to rewrite it. I'm going to rewrite it as 1 over 30h times dv dt. Same thing as that. And so now dh dt is equal to 1 divided by 30 times 1/2 times 12. This is going to be 15, so it's going to be 12 divided by 15. dh dt equals to 12 divided by 15, which reduces to 4/5, which reduces to 0.8, and this is feet per minute. Feet per minute. So the water level is rising at a rate of 0.8 feet per minute. Okay, so we have our trough. We're pouring water at a rate of 12 cubic feet per minute, that is dV dt, right? It's positive because we're increasing the volume. And we were able to figure out a formula for dH dt, where h represents the height of the water line, right? As we see in our picture here, the entire shape, the shape of this trough has a height of 1 foot, but the water line is going to be much smaller than that. As it's rising, it's approaching 1 foot. But we've established now that when we plug those guys in, the water level will be rising at a rate of 0.1 feet per minute. That's the speed at which it's rising when h equals to a half a foot, right? So a half a foot is halfway through, right? The whole thing is only 1 foot tall. So when h equals to half a foot, 1/2 feet, then you're halfway through the trough. And at that point in time, the speed, the rate at which the water line is rising is going to be 0.8 feet per minute. Good. Okay, so hopefully this is enough to get you started on these questions. Please don't hesitate to come to my office hours if you have any questions about any of these guys.